We've all been there. You're signing up for a new website, you're excited to join, you find the perfect username, then you hit check availability. Your heart sinks. That name is already taken. Frustrating, isn't it? Behind the scenes, the website needs to check if your chosen username already exists. This seems simple, however, with millions of users, it can become a time-consuming task. This is where Bloom filters come in. Bloom filters are like clever shortcuts, allowing websites to perform these checks remarkably fast. Traditionally, websites use methods like linear or binary search to check for existing usernames. Imagine searching for a name in a phone book. Linear search is like flipping through every single page. Binary search is smarter, like flipping to the middle and narrowing down the search. But what if there was a faster way? Bloom filters offer a revolutionary approach. They sacrifice a bit of accuracy for incredible speed and efficiency. Instead of storing all usernames directly, Bloom filters use a much smaller fingerprint to represent them. This makes checking for duplicates incredibly fast, especially for large data sets. Imagine a light switch. It's a simple device, right? You can either flip it on or off. This binary state is fundamental to how computers process information. It can be either on or off, representing 1 or 0. This is the essence of binary code, the language of computers. Bloom filters work with a similar concept, using a string of bits, zeros and ones, called a bit array. This bit array is like a digital representation of multiple light switches. Think of it as a row of light switches, initially all turned off. Each switch represents a bit in the array, starting in the off position. When a new username is added, it goes through a special transformation called a hash function. This function is like a digital fingerprint, unique to each input. This function generates a unique code for each username. Think of it as a unique identifier that helps in locating the exact position in the bit array. Based on this code, specific light switches in the bit array are turned on. This marks the presence of the username in the filter. The more usernames are added, the more switches are flipped on. However, there's a catch. As more and more usernames are added, the likelihood of multiple usernames flipping the same switch increases. Multiple usernames might end up flipping on the same switch. This overlap can lead to a situation where the filter indicates a username is present when it isn't. This is where the trade-off comes in. Bloom filters are designed to be space efficient and fast, but this efficiency comes at a cost. Bloom filters are incredibly space efficient and fast, making them ideal for applications where quick lookups are essential. However, they can sometimes give false positives. This means the filter might say a username is taken when it's actually available. Despite this drawback, Bloom filters are widely used in various applications due to their efficiency and speed. Let's break down how a Bloom filter works. First, initialization. We start with an empty bit array, all bits set to 0. Next, adding a username. When a new username is added, it's processed by multiple hash functions. Each hash function points to a specific bit in the array. All these bits are set to 1. Finally, checking for a username. To check if a username exists, the same hash functions are used on the username. The hash functions point to specific bits in the array. If all these bits are 1, the filter says the username is probably taken. If any of these bits are 0, the username is definitely available. Section 5, from words to bits. A practical example. Let's visualize this with an example. Imagine our Bloom filter has a bit array of 10 bits. We want to add the usernames geeks and nerd. First, adding geeks. Our hash functions point to bits 2, 5, and 9. These bits are set to 1. Next, adding nerd. The hash functions point to bits 1, 4, and 7. These bits are set to 1 as well. Now, our bit array looks like this. 0, 110, 110, 101. Notice that some bits are shared. This is where the possibility of false positives arises. Section 6, the mystery of false positives. Understanding the glitch. Let's say we want to check if the username cat exists. The hash functions might point to bits 2, 4, and 9. We see that these bits are already set to 1, even though we never added cat. This is a false positive. The more usernames we add, the more switches are turned on in our bit array, increasing the chance of a collision. We can control this by using a larger bit array or more hash functions. Section 7, the language of Bloom, filters. Deciphering the formulas. Bloom filters come with their own set of formulas. to calculate important factors. These formulas are essential for understanding how Bloom filters work and for optimizing their performance in various applications. First, we have the false positive probability, often denoted as P. This is a crucial metric because it tells us the likelihood of the Bloom filter incorrectly indicating that an element is present when it is not. This tells us the likelihood of getting a false positive. Understanding this probability is vital for applications where accuracy is paramount, such as in network security or database querying. It depends on the bit array size, the number of inserted elements, and the number of hash functions. Each of these factors plays a significant role in determining the efficiency and accuracy of the Bloom filter. The formula is P equals 1 minus e to the power of negative kn over m, all raised to the power of k. This formula might look complex, but it essentially helps us understand how the parameters interact to affect the false positive rate. Next, we have the optimal number of hash functions, symbolized as k. The number of hash functions is critical because it influences both the speed and accuracy of the Bloom filter. This formula helps us find the ideal number of hash functions to minimize the false positive rate for a given bit array size and number of elements. By optimizing k, we can ensure that the Bloom filter performs efficiently without unnecessary computational overhead. The formula is k equals m over n times the natural logarithm of 2. This equation provides a straightforward way to calculate the optimal number of hash functions based on the size of the bit array and the number of elements. Lastly, we have the bit array size, represented as m. The size of the bit array is a fundamental parameter that affects the overall performance and accuracy of the Bloom filter. To achieve a desired false positive probability, and knowing the number of elements, we can calculate the required bit array size. This calculation is crucial for designing Bloom filters that meet specific performance criteria. The formula is m equals negative n times the natural logarithm of p, all divided by the natural logarithm of 2 squared. This equation helps us determine the bit array size needed to achieve a particular false positive probability. These formulas help us fine-tune the Bloom filter for specific needs. By understanding and applying these equations, we can design Bloom filters that are both efficient and effective for a wide range of applications, from data storage to network security. Section 8. A balancing act. Weighing the strengths and limitations. Bloom filters offer compelling advantages. They are particularly useful in scenarios where memory efficiency is crucial. By using a Bloom filter, you can significantly reduce the amount of memory required to store data, which is a huge benefit in environments with limited resources. They are space efficient, using significantly less memory than storing complete data. This makes them ideal for applications like network routers, databases, and even blockchain technology, where memory usage can be a limiting factor. They also provide fast lookups, checking for elements incredibly quickly regardless of the dataset size. This speed is essential for real-time applications where delays can be costly, plus they guarantee no false negatives. This means that if the filter indicates an element is not present, you can be absolutely certain it isn't. If the filter says an element doesn't exist, it definitely doesn't. This reliability is crucial for applications where accuracy is paramount. However, they come with a trade-off. While Bloom filters are efficient and fast, they are not perfect. Bloom filters can sometimes indicate an element exists when it doesn't, leading to false positives. This can be problematic in scenarios where false positives can cause significant issues, such as in security systems or critical data processing. Additionally, removing elements is not directly supported, as it might impact other elements sharing the same bits. This limitation means that once an element is added, it cannot be easily removed without potentially affecting the accuracy of the filter. The choice of using a Bloom filter depends on whether the benefits outweigh the limitations in a specific application. Careful consideration is needed to determine if the trade-offs are acceptable for your particular use case. Section 9. Bloom filters in action, real-world applications. Bloom filters are used in various domains. They are employed for checking username availability quickly, determining if a username is already taken. In web caching, they help determine if a web page is already stored in the cache. For spam filtering, they identify and block known spam email addresses. In network security, they detect and prevent malicious IP addresses from accessing a network, and in database optimization, they quickly check if a query result is already cached before hitting the database. These are just a few examples of how Bloom filters are used to improve efficiency in different fields. Section 10, the power of probabilities, choosing the right tool. Bloom filters are not a one-size-fits-all solution. They are incredibly powerful when used strategically. If your application requires absolute accuracy, Bloom filters might not be the best fit. However, if you're dealing with large datasets and speed is crucial, Bloom filters become an invaluable tool. They allow you to save space and time, accepting a small possibility of false positives. The key is to understand the trade-offs and choose the right tool for the job. Bloom filters, with their probabilistic nature, offer a unique and efficient solution to many real-world problems.